So hopefully by now you have some idea of electric fields and sort of what they look like and how they're created around positive and negative charges. Let's do some math with them now. I actually want to start off going back to gravity and our gravitational force. We have this equation for gravity, Newton's law of universal gravitation, as this: m1, m2, over d squared, right? But that's not the equation we usually use to determine the gravitational force on an object, because on Earth, we know the gravitational field strength is always around 9.81. So what we do is we simplify this equation to this: Fg equals the mass of the object times the acceleration due to gravity, right? And another way to call this acceleration due to gravity is the gravitational field strength. Right? And what the field strength really is, it's the amount of newtons of force applied to a 1 kilogram object, right? So it's like the newtons per kilogram. And the way we get that is by plugging in like the radius of Earth and the mass of Earth into this equation, and we basically simplify these three parts of the equation as 9.81 on Earth. So it's like we're basically we're simplifying the equation to come up with this if we know the field strength. We can do the same thing for the electric force. So we know the electric force is equal to K Q1 Q2 over R squared. So if we know the strength of the electric field, we can simplify these terms here if we know how strong the field is per coulomb of charge. And the way we can simplify the equation is in the same way. So the electric force is going to be the field strength times the charge. The symbol we use for field strength is epsilon times the charge. Epsilon is a Greek letter. It just looks like a curly E basically. But again, it's just the field strength of the electric field. And the units that that field strength will have, it will be E in newtons per coulomb. So it's basically how many newtons of force are applied to any coulomb of charge in the field. So this equation, you'll see if we know the field strength, is going to be a lot simpler to use to calculate the magnetic force, or sorry, the electric force on an object. So right here, that's basically the equation we can come up with. Here's two parallel plates with charges, one positively charged, one negatively charged. So we know that the field, the magnetic field, or the electric field, I keep saying magnetic, the electric field is going to go in this direction, right? From positive to negative. So we can call the field strength epsilon as that, and it does have a direction. It is a vector, right? The field does have a direction. And we're basically saying if we put a charge in that field, the force that's applied on it, where's my blue? The force, actually let's use red. The force that's applied on it is just going to be the amount of charge times the field strength, the epsilon. Okay? So it's very similar to how we would, how we would find the force of gravity on an object, on a mass in a gravitational field, right? It's basically the same thing. So if we look back at that equation up here, we can see what we made epsilon. We made epsilon these things. So basically, epsilon is K Q over R squared, right? Where Q is like the charge that's creating the field, right? This is the charge that's creating the field. But the useful relationship we have for this is that the electric force is just going to be equal to, and this is a vector, is equal to epsilon times the charge that you're putting in that field, right? So there we go. That's a little bit of a simpler way to put it than, a simpler calculation if we know the field strength than using Coulomb's law. And again, the unit, for field strength is newtons per coulomb. Okay? So let's do a question. Assuming the electric field strength of parallel plates above is 0.02 newtons per coulomb, determine the acceleration of a single proton in the field. So if we have a proton in this field, right, I'll put a P positive for proton. For something to accelerate, it needs to have a force applied to it. And we know the force is going to be applied to the proton. Now, which direction is the force going to be applied? Well, a proton in this field, you know the proton is going to follow the electric field lines. It's going to be pushed downwards, right? Because it's going to be attracted to the negative at the bottom, right? So the force, the electric force, is going to be in this direction, right? And the magnitude of it is going to be epsilon, or the field strength, times the charge. Then we can figure out the acceleration, but first we need the force. So first of all, we need the epsilon. We have the epsilon. We need the charge of one proton. And the charge of a proton, it's something you can look up. It should be on your formula sheet. If it's not, I will make sure it's on your formula sheet. But the epsilon is 0.02, and that's newtons per coulomb. And the charge of a single proton is 1.60 times 10 to the negative 19 coulombs. So the force here, clearly it's going to be a very, very small force, right? Because the field isn't that strong, but also the charge of a coulomb is very strong. So if we do that, we get that the force is 3.2 times 10 to the negative 21. And that's in newtons, right? Because, again, the field strength was in newtons per coulomb. Sorry, you can't really see that. I know I didn't give you much space for this question. Sorry about that. If you're doing this on a piece of paper, it's your lucky day. You can take as much space as you want. So we know the force now applied to that proton, but now we need to find the acceleration, right? The acceleration, we know, according to Newton's second law, is going to be the net force over the mass, right? So now we know the net force. By the way, you'll notice we're ignoring gravity here. And there's a very good reason for that. That the force of gravity is going to be tiny, tiny, tiny. It's going to be negligible on a proton. And we also aren't given any indication of what direction down is in this example. We don't know if these two plates are horizontal or vertical or whatever. So let's just ignore gravity for the sake of finding the F net here. So we need the mass of a proton. And that's another thing that you can look up. And the answer to that is 1.6. So we'll plug that in. The F net is 3.2 times 10 to the negative 21 newtons. And then the mass is 1.6 times 10 to the negative 27. Both very small numbers. Kilograms. So this is kilograms, this is newtons. And when we divide those, we are going to get 2.00 times 10 to the 6 meters per second squared. And we know the direction is it's downwards based on our drawing. So that's a lot of acceleration, even for such a small magnetic field. Why is it so small? Well, think about your Newton's second law. We have a tiny, tiny, tiny mass. And that's basically the reason why it's so small, is because the mass of a proton is so small. So even a small force will will be like a huge force compared to that tiny mass. So that's how much it'll accelerate. Now, what's the acceleration? The next question, the acceleration of a single electron in the field, in that same magnetic field. Sorry, electric field, I should say. Well, let's think about, is it going to be any different? Is it going to be the same? Well, remember, an electron has the opposite charge. So instead of moving down in that field, an electron is actually going to move up in that field, right? So if we have our electron here, the force on it is actually going to be in the opposite direction. And we can just do that by looking at it, basically. It's in the opposite direction of the magnetic field. And that's what electrons do. They go in the opposite direction of the electric field. Sorry, I keep saying magnetic. So how do we calculate this? Well, it's the exact same process, right? The force is just in the opposite direction. Now, notice, the charge of a proton and the charge of an electron are the exact same thing, right? They're equal and opposite to each other. One's just positive and one's negative. So the force on an electron is actually going to be the same as the force on a proton, just opposite signs. So we can say the electric force on that electron is going to be negative 3.2 times 10 to the negative 21 newtons, right? It's just going to be going upwards instead of downwards. But the force is the same because the charge of a proton and electron are the same, right? One electron and one proton cancel each other electrically. And then we can calculate the acceleration. Now the question is the mass of an electron the same as the mass of a proton? And the answer to that is no. Electrons are actually much tinier in terms of mass. They're much less massive than a proton. And the mass of an electron is actually 9.1 times, let's put the force first. So negative 3.2 times 10 to the negative 21 over the mass of an electron is 9.11 times 10 to the negative 31. So it's many orders of magnitude smaller than the mass of a proton. And we can calculate that. Negative 3.2 times 10 to the negative 21 divided by 9.11 times 10 to the negative 31 is, that's a big number. Negative 3.5, let me write it over here. Sorry, I didn't give myself enough space here. Negative 3.5 times 10 to the 9 meters per second squared. Right? Now the negative just is telling us direction, right? It's telling us it's going up. As long as you're clear about that, it doesn't really matter. You don't need to put the negative. You could just put 3.5 times 10 to the 9 meters per second up. All right? Then you don't need to include the negative. But notice how this is a much faster acceleration than the proton. And that's, of course, because electrons are much less massive. This was 3.5 times 10 to the 9. This was times 10 to the 6. So it's like 1,000 times, right, more acceleration than the proton had. There we go. And lastly, if a proton starts at the positive plate, determine the speed it will be traveling when it reaches the negative plate. So if the proton is starting up here and it reaches down here, how fast will it be going if it starts at rest up here? And, even though these particles are really small, they're still going to generally obey Newton's laws, right, and our kinematic equations. So we can look at this as sort of our starting point right up here. It's going to have some initial velocity of 0, right? It's going to be starting at 0. When it gets down to the bottom, it will have been accelerated that whole time. So it's going to have some big VF, right? And it's telling us the gap, the delta D between those two plates, is 3 millimeters, which is 0.003 meters. Now the question I'm going to ask you is this acceleration that we calculated for the proton, can we just use that number? Is the field going to be constant? And the answer is, between two plates like this, we usually assume that the electric field that's created is going to be a constant value. So the acceleration, or the force that's applied on that proton, is going to be a constant value. So yes, the acceleration will be constant. So we knew that. We calculated it over here. So we should just be able to use one of those 5 kinematic equations of uniform acceleration to find the final speed. So pause the video here, try to find the answer. When you're done, unpause it, and I will reveal the answer. So there's the answer. It should be about 110 meters per second down. So you see, even in that tiny little amount of space, the 3 millimeters, the acceleration was so large that it was able to accelerate very, very, very fast. And again, the reason that all these protons and electrons and stuff like that move at such high speeds is because their masses are so low. So they have, even small, even tiny forces are able to accelerate them very fast. There you go. The thing to remember about questions like these is that electric questions and stuff, you can't see it on a daily basis. Like, you can't see protons and electrons. But remember, they just follow the exact same rules as objects do. At least we're going to assume they follow the exact same rules that objects do when moving in gravitational fields. So it's really the same calculation that you would be doing for a mass in a gravitational field or for a proton in an electric field. The only difference is that you have to be careful about the direction it moves, because in electric fields you can have things attracting as well as repelling. All right, there we go.